Some fascinating facts from the non-Archimedean world. Hello friends, in this video we share a few extremely interesting facts from the world of non-Archimedean metrics and norms. Given a non-empty set X, a function d from x cross x to the set of non-negative reals is said to be a metric or a distance function on X if the following conditions are satisfied for all x, y, z in X. Number 1, dxy is 0 if and only if x equal to y. Number 2, dxy equal to dyx. And number 3, dxy is less than or equal to dxz plus dzy. This is called triangle inequality. A metric d on X is said to be discrete if dxx is equal to 0 and dxy is equal to 1 for all x not equal to y. A metric d on X is called non-Archimedean or an altimetric if the following strong triangle inequality holds for all x, y, z in X. The condition is dxy is less than or equal to, instead of sum of dxz and dzy, it is the maximum of dxz and dzy. This is called altimetric inequality or strong triangle inequality. For example, discrete metric is non-Archimedean. The altimetric inequality is indeed stronger than the triangle inequality. That's a easy exercise. A set X equipped with a metric D is called a metric space and is denoted by XD. In particular, we talk about non-Archimedean metric spaces or altimetric spaces. In a metric space XD, the triangle inequality dxy less than or equal to dxz plus dzy is called so because it says that the sum of two sides of a triangle is greater than the third side. This can be seen in the following diagram. We have a triangle whose vertices are x, y, z and whose sides are dxy, dxz and dzy. Triangle inequality says that this side is less than or equal to sum of these two sides. Okay. In a non-Archimedean metric space, we have the following amazing result. In a non-Archimedean metric space, every triangle is isosceles and the length of the base does not exceed the lengths of the other sides. This means that every triangle is like this. Here you can see this base is smaller than these two sides, or it may be like this where all sides are equal, but it is never like this where base is bigger. Proof. Let xyz be the vertices of a triangle in which dxy is less than dxz. By the altimetric inequality, we have dxz is less than or equal to maximum of dxy, dyz. Y is introduced here. But this assumption says that dxy is less than dxz. Therefore, this maximum value cannot be equal to dxy. Otherwise, dxz will be less than or equal to dxy. So, this maximum value must be equal to dyz, which means that dxz is less than or equal to dyz, and this is because of our assumption. Okay, dxz is not less than or equal to dxy. It is in fact greater. Again, using the altimetric inequality and our assumption, we have dyz is less than or equal to maximum of dxy dxz. x is introduced, but this is bigger by our assumption than this, so it is this. Thus it follows that these two quantities are equal. Whenever two sides of a triangle are unequal, the longer of them equals the third side. Okay. Another interesting result in an ultrametric space is as follows. In a non-Archimedean metric space, every point lying in a disk, open or closed, is a center of the disk. In other words, every point in a circle is a center. That's quite amazing. Proof. Consider a disk DAR, which is the set of all x such that dxa is this is either less than or equal to r, with center A and radius r. Here this particular symbol stands for any one of these two symbols. Okay, you can use this in place of this or this in place of this, both will work. Let B be any arbitrarily chosen point in this disk. Okay, we choose a point B here in this disk. Then for all x in DAR in that disk, we have by ultrametric inequality dxb is less than maximum of dxa dab. A is introduced, but both of them are less than r, so it is this r, less than or equal to. This means that here x was a arbitrarily chosen point in this disk, so this is less than or equal to dbr. This is a subset of dbr. Similarly, we have dbr, this disk with center B and radius r is a subset of dar, and hence the equality. The sets X will be dealing with will mostly be fields. So the underlying set of the metric space will be fields in most of the occasions. Recall that a field is a set together with two operations plus and dot such that F is an abelian group under plus, non-zero elements of F form an abelian group under dot, and dot is distributive over plus. That is the distributive law. The examples of a field we have in mind at this point are the field of rational numbers, the real numbers, and complex numbers. Our metrics on a given field will all come from the norms on that field. A norm on a field F is a function, this double line, from F to non-negative reals, such that the following conditions are satisfied for all xy in F. Number 1, norm of x is 0 if and only if x is 0. Norm of x dot y is equal to norm of x into norm of y. This multiplication is in the non-negative reals, and this is field multiplication. And the last one is triangle inequality, that is norm of x plus y is less than or equal to norm x plus norm y. This is triangle inequality. A norm on F is said to be trivial if norm of 0 is 0 and norm of x is 1 for x non-zero. A norm on a field F is said to be non-Archimedean if it satisfies the following strong triangle inequality. This is the strong triangle inequality. Norm of x plus y is less than or equal to maximum of norm x, norm y for all xy in F. This is also called ultrametric inequality or strong triangle inequality. For example, trivial norm is non-Archimedean. The ultrametric inequality is indeed stronger than triangle inequality satisfied by a norm on a field. Again, this is a easy exercise. a norm or a metric which is not non-Archimedean, that is ultrametric inequality fails, is called an Archimedean norm or an Archimedean metric. So Archimedean norm and Archimedean metric means the ultrametric inequality, that means the strong triangle inequality, fails, doesn't hold. Only triangle inequality holds. Okay. And of course the first two conditions also. Every norm on a field F induces a metric D on F defined by dxy equal to norm of x minus y. X and y are elements of F. If the norm is non-Archimedean, then so is the induced metric D. That means a non-Archimedean norm on a field F induces non-Archimedean metric on that field. Also, if the norm is trivial, then the induced metric is discrete. A basic example of a non-trivial norm on the fields Q, R and C is given by the absolute value of X, for which the induced metric is the usual concept of distance in rationals, reals and complex numbers. This is in fact an example of an Archimedean norm or metric on Q, R and C. Before we proceed any further in this topic, it is necessary to give an example of a non-trivial norm that is non-Archimedean. We will do that in our next video, which will be uploaded very soon. In fact, we will talk about p-adic norm. That's all for now. If you like this video, then please subscribe and share my channel for more of such videos. Thank you.